Good day, ladies and gentlemen, and welcome to the Weatherford webcast on Offshore, Proven, Accepted, Expected, the first of a four-part Managed Pressure Drilling MPD webcast series. I am Jules Marchon S. Torralde. I am the Global Deepwater Managed Pressure Drilling Champion of Weatherford. I have been with MPD since 2005, and I have participated in the delivery of globally pioneering projects on MPD in Indonesia, Brazil, Malaysia, Angola, and Spain, and I am still actively supporting the integration of MPD technologies in offshore drilling rigs and deepwater drilling environments. We are saying that offshore managed pressure drilling is proven, accepted, and expected because we have case histories that support the adoption of the technology in different environments, in different rig types, and across all the phases of the life of the well. It is accepted because the operators and the rig contractors that have used the technology have realized that it is a technology that makes the drilling process better, and they have continued using the same. In fact, most of the operators that have used MPD are expecting that the rigs that they will be using will have MPD capabilities and are even requiring the same. As a technology, MPD is now entering the phase of mainstream adoption, and this is supported by improved regulation and permanent installations on the rigs themselves, even in deepwater ones. It is becoming the new drilling convention. The adoption of MPD technology has not been immediate. It started in 2003 when the industry accepted the terminology of managed pressure drilling as a means of a way of being able to drill wells that are difficult to drill. So essentially, if you can see in this graph, how can I drill this well, or drillability was the main driver that made operators and rig contractors use managed pressure drilling methods. Later on, as MPD methods and approaches evolved, it became an issue of efficiency. How can I drill this well better? How can I improve the economics of this well? And that added more adopters of the technology. But essentially, the main thing that happened recently is that we had the Macondo incident on April 20, 2010. And from that point on, people have been using, or at least entertaining the use of MPD in order to be able to drive process safety better across their operations. MPD is able to do that, and we will expound later on as to how it is able to improve process safety on top of drillability and efficiency. So overall, the adoption of MPD technology now addresses all of these three drivers of the technology. I'll repeat. Drillability, efficiency, and safety are the main drivers of MPD technology adoption. But what is MPD, and how does it make problems disappear? The International Association of Drilling Contractors, or IADC, defines managed pressure drilling as an adaptive drilling process used to more precisely control the annular pressure profile throughout the wellbore. It is in sense saying that with MPD, you have active control of the bottom hole pressure profile of the well, and you can change it quickly, immediately, efficiently, allowing you to react to problems and address events as quick and efficiently as possible. The same definition says that it has two objectives. Number one, to ascertain or to know the downhole pressure environment limits, and number two, to be able to manage the annular hydraulic pressure profile accordingly. So MPD is not just about managing bottom hole pressure, it's also about knowing what are the limits of the geopressure environment and staying within those limits to be able to drive safety, efficiency, and drillability in the process. What makes MPD different from conventional drilling? Well, essentially, it's a matter of what is open and what is closed. What can you do in this particular circumstances? Conventional drilling essentially exists in an open to the atmosphere system. The well is open to the atmosphere whenever drilling occurs. And bottom hole pressure, because it's open to the atmosphere, is only manipulated by the mud weight that is in the well that provides pressure at the bottom of the well and friction when the pumps are running. Only those two factors. Managed pressure drilling changes that by making the system a closed and pressurizable system. Being able to do that allows you to make quick bottom hole pressure adjustments. If you look at the equation on the right, we are now able to add back pressure as a factor of what can influence bottom hole pressure. And back pressure, unlike mud weight, can be changed quickly and immediately, which means you are able to adjust to whatever events are encountered during the drilling process more quickly and dispose of the same. Now, why do we need to be able to react quickly to downhole events? Well, we have this slide here which shows us that the ultimate objective is to be able to drill and maintain a stable wellbore, a Goldilocks phase, if you might call it that, Not too hot, not too cold, no influx, no kicks, just right, a stable wellbore. And that is what MPD gives us. The graphic on the left side of this slide shows that if pressure on the well is too low, you risk having a major kick or blowout. Fluids will enter the well and come at you. Or you are unable to maintain pressure on the well to be able to keep it stable, and it will start to fall on you, causing you to get stuck. On the extreme side, of the right side of this slide, you have hole ballooning whenever you're exerting too much pressure that the rock can no longer stand the said pressure and starts to fracture. If you add more pressure to it, you will essentially be breaking the rock and causing circulation losses into the well, which, if left alone, will also produce a kick, giving you problems. We realize that if we are able to detect these problems immediately, then we are able to address them quickly. But with conventional methods, that is not usually the case. MPD changes that and allows you to immediately react to all these changes if detected. Now, MPD can do all this, but how do we integrate it into conventional rig operations? So where is it located? In the offshore MPD system. So this particular diagram shows you where the components are. The first major component is on the left side, the rotating control device, or the RCD. What it does is it diverts flow instead of going from the bottom of the well to the annulus and through the diverter. It's now diverted towards the next key component, which is the automated MPD manifold. All the flow of the well is diverted by the rotating control device towards an automated MPD manifold. The annulus is also sealed by the rotating control device. I will show you a picture later on as to how it does this, as well as a picture of the automated MPD manifold. We monitor what happens with the well on the automated MPD manifold. It has a mass flow meter which detects what is the flow, what is the density, what is the temperature coming out of the well. We then compare this using software, using a program and using an automated MPD control system as to what is coming into the well. Like what are we pumping into the well? We then compare those two values and be able to see whether, one, we're having a kick or an influx, and on the other side, whether we are already having losses. Once we see it, the automated MPD manifold is also able to adjust to it. I will share with you the components of the said automated MPD manifold and what it does in later slides. Going back to the RCD, or rotating control device, we have a picture here on the left. It's composed of a bearing assembly, which is the one on top, and the RCD body, which is the one below. The RCD bearing assembly seals on drill pipe, allowing us to close the annulus off when the bearing assembly is installed within the RCD body and retained by the same. Doing that allows us to divert the annular flow of the well being drilled, and the RCD also serves as a barrier between the well and the rig floor at various amounts of pressure. All in all, the RCD allows us to drill with pressure on the well because there are bearings on the said bearing assembly, allowing rotation at the same time closing the well off so we can exert back pressure. There is a standard. As we said, there is regulation with regards to managed pressure drilling already, and the one for the RCD is called API 16 RCD. With this standard, everybody can compare as to how much their rotating control device can take at whatever rotational speeds. The next slide showcases how the RCD works. For those who are strong on the visual learning side of things, this is our animation on the rotating control device. It shows an RCD in the deep water scenario. We have hydraulic control of the same, and it's integrated into the riser system. This is a deep water setup, and essentially within that RCD you have the bearing assembly installed, and it rotates with the drill pipe with pressure on the well. All flow is diverted towards the MPD automated manifold so that we can detect and process what is going on with the well, and we can immediately react if there are any deviations from the norm. Now that the RCD has handed off flow towards the automated MPD manifold, what do we do with it? We first have a detection skid where we have our instrumentation. We mentioned a Coriolis mass flow meter. The mass flow meter allows us to detect with precision as to what's going on with the well in terms of flow, and we also have other sensors which monitor pressure. If there are deviations detected, we have the ability to be able to manipulate the bottom hole pressure of the well using the chokes, which there are normally two, on the control manifold of the automated MPD system. What you don't see here is an intelligent control unit of which the software processes all of this information and enables us to immediately warn the driller or the operator of the system if there is a kick, if there's a loss, and at the same time, it can even automatically adjust to the said event so that its impact is minimized and its consequence mitigated. Now, how do we practice MPD? MPD has a lot of variants, and I'm going to introduce you to at least 4 of the common ones. Just as a reminder, the goal of MPD is to control the pressure profile in a way that we eliminate many of the drilling and wellbore stability issues that are inherent in conventional technologies. The first one is returns flow control, or the safety side of MPD. In this, we reduce the risk to personnel and environment by monitoring what is going on with the well and being able to react to them quickly. The second one is pressurized mudcap drilling, or PMCD. This is a type of MPD we use when we are drilling in extreme loss situations so that we can drill ahead safely and efficiently. Constant bottom hole pressure is more geared towards narrow mudweight windows, wherein you don't have severe circulation losses, but you have a need to be able to navigate narrow drilling geopressure environments because certain formations have characteristics that are not readily addressed by conventional methods. CBHP allows us to address the same. And the fourth one is dual gradient drilling. All it essentially does is it establishes two or more gradients within the riser, because this is more geared towards deep water, allowing us to manipulate the bottom hole pressure with the same. Let's discuss returns flow control in detail. Essentially, as a review, with a rotating control device, we create a closed and pressurizable system, and all flow is diverted towards the automated MPD detection and control manifolds. And with our high-resolution mass flow meters, and by monitoring certain crucial parameters within the drilling environment, we are able to immediately detect, we are able to increase the sensitivity of the drilling monitoring system to kicks, losses, and other events. With the returns flow control mode of MPD, we are able to do advanced and early flow detection and even control. And we are also, from a deep water perspective, able to address riser gas and mitigate against the same. Pressurized mudcap drilling is a variant of MPD that involves drilling without any returns to surface. Essentially, there is an annular fluid column which is underbalanced compared to the pressure that the well exerts, allowing us to be able to maintain it in the annulus. And since it's underbalanced and the well is fully closed off with the RCD, there is positive pressure at surface, and we use that pressure to be able to determine what is going on with the well. All the formation, if you go back to the previous slide, all the cuttings and all of the formation fluids are actually diverted into the formation where the losses have been found. And this is particularly possible if you are drilling through highly permeable formations. So essentially, PMCD is what we use to be able to drill through severe circulation losses efficiently and safely, because we have monitoring capabilities despite of the same. The next one is constant bottom hole pressure, but before we proceed, I'd just like to reach out to those who already know about the basics of MPD, that we do have the main part of the presentation, which are the case histories coming up. So if you'd indulge us a bit further, we will continue with the basics, a few slides more, and then we'll move on to the case histories. So going back, we do have constant bottom hole pressure as the third common type of MPD. And essentially, if you have a large drilling window, even if you're making connections, which are the dips in the graph that you see, you are within the drilling window, and you are not inviting kicks and losses as you drill, even when the pumps are turned off and the bottom hole pressure drops, because your friction disappears. However, if you have a narrow mudweight window, then essentially when you make a connection, you are below the pore pressure, which is the blue part of the line here. The blue dotted lines that are here presents pore pressure. So if you are making a connection, you invite the possibility of a kick. With constant bottom hole pressure, as you can see, it's more or less aligned, allowing you to stay within the narrow mudweight window. We do this by exerting back pressure to substitute for whatever friction is lost when making a connection, thereby allowing us to keep bottom hole pressure constant. And lastly, dual gradient drilling is essentially a means of separating the gradients of the fluid while you are drilling. And from a Weatherford standpoint, we are involved in the same with the provision of a subsea rotating control device, or the SRD, which allows diversion of fluids so that a dual gradient environment can be established. And that is the picture you see here. Now that we've established the basics of MPD, we now move on to the case histories. This is to show you how offshore MPD has progressed to cover any rig type and how it has been applied in the same. It has been applied on land rigs, jack-up and tender rigs, semi-submersibles, and more recently on dynamically positioned drill ships. So essentially, MPD on any rig type, proven. This is a picture of a deployment on a land rig, which is pretty common wherever we are. MPD is being used to be able to drill safely, and in certain instances, certain drilling operations are not even allowed to proceed if an RCD is not installed from a safety standpoint. The next slide shows that MPD operations have taken place on a lot of jack-ups and tender rigs. Whether for PMCD or CBHP purposes, MPD has become a staple in certain critical environments that are drilled using a jack-up. MPD has also moved on to semi-submersibles and floating rigs, whether they are moored or dynamically positioned, and we have deployed the same. In this particular picture, we are showing an above tension ring application of MPD, and we are installed right above where the tension ring is. And since the rig is not rotating, we are able to keep our hoses and all our tie-ins to the MPD system above the tension ring. However, when the rig does rotate, we do need to have a different type of RCD to be able to interface with a dynamically positioned drill ship which rotates in relation to the weather as it drills a well. So essentially, with a below tension ring rotating control device, as shown in the picture here, we are able to interface with DP drill ships and DP semi-submersibles, and we even have bypass lines now installed, not shown in this picture. We now have bypass lines that can go through the MPD joint so that we are able to install below the termination joint and therefore remove another barrier for adoption for MPD in the deep water environment. So that is MPD in all types of rigs. It's a proven and it is a field-ready technology for any type of rig. We now discuss how has MPD been used across the life of the well. It might surprise some, but MPD is actually used whether it's exploration, appraisal, development, and intervention, because safety and efficiency does not choose any particular phase in the life of the well. From an exploration standpoint, MPD was used in Indonesia for multiple deep water wells at a water depth of around 6,000 feet to be able to manage geopressure environment uncertainties and associated risks in wildcat wells. In this particular case, the wells that were drilled had very few offset information to which to base what the geopressure environment is. So MPD was needed to be able to immediately react to whatever the well would give the drilling operator. With MPD, you can rapidly and accurately apply and manage backpressure to determine what is the actual pressure profile of the wells, because with minimal offset data, you will not know what to expect. But with MPD, you're able to adjust to whatever the well gives you, whether it's detection and control of kicks, and in this case, we even had total losses in at least 2 of the wells allowing drilling to proceed in a deep water environment in severe circulation losses. Despite of these losses, the well was even successfully logged and evaluated. So that is our case history for exploration. There are a few more, and in the resource folder that we will be providing, there will be a whole lot of other case histories in offshore MPD as to how it has helped in the exploration phase of drilling operations. This next case history is from the southwest Gulf of Mexico, particularly when drilling through medium Cretaceous and lower tertiary formations. It was an appraisal well, and with MPD, they were able to drill successfully in areas that have challenged conventional drilling methods. Whenever TD is not reached, the next well, one of the technologies that is immediately considered is, of course, MPD. In this particular instance, using the constant bottom hole pressure variant of MPD, the well was drilled with no loss of circulation in a far shorter time frame than initially allotted. Drilling time was reduced from 30 days to 5 days, a savings of 83%, and mud savings exceeded more than $1 million. MPD engineering was applied to be able to continuously provide hydraulic stimulation, and it increased the drilling efficiency by mitigating drilling hazards. So, from an appraisal standpoint, MPD gets you where you need to go at a fast and efficient manner. We now go from the Gulf of Mexico to our friends in the Middle East. This is in offshore Oman on deviated wells and through the Ilam, Lafan, Mishrif, Kathia, and Madud limestones. In this particular instance, which is from a development and production standpoint, TD, or target depth, for 3 wells was reached by mitigating conventional drilling non-productive time issues such as lost circulation, differential sticking, and well control incidents. MPD is production friendly, and it equipped the operator to handle numerous contingencies. It also allowed them to use lighter mud weights and to determine precise formation pressure limits. Non-productive time, of course, was severely reduced, and the safety of the operation was top-notch. The fourth one, which is on the intervention phase of the life of the well, addresses how MPD allows safe and efficient re-entry of abandoned wells with well integrity issues. In this particular case study, we were able to safely re-enter and properly abandon an offshore development well in shallow water because it was leaking from previous isolation methods deployed. MPD was used to cap the well and immediately detect an influx of gas during the re-entry operations once the isolation plugs which were leaking were drilled out. Using MPD to enhance surface monitoring allowed for proper risk mitigation, and immediate action was taken to secure the well if and when required. And that is how MPD was deployed from an intervention standpoint. So whether it's exploration, appraisal, development, or intervention, MPD has its use and its niche to be able to enhance safety, efficiency, and process safety from an overall standpoint. MPD is also applicable across all types of geological complexities. All the easy wells are gone, and all the wells that are left are challenging wells, whether they be through carbonate, high pressure, high temperature clastic wells, or through subsalt formations wherein we do not essentially know what is underneath the salt. MPD is able to assist in drilling the same. This is a case study in Angola, drilling through carbonate formations, where MPD was used to address severe circulation losses to provide multiple efficiency and safety benefits over conventional methods. In this case, it was used to drill an oil well with 1 to 2% H2S on the Middle Pinda highly fractured formation. Losses of as much as 720 barrels per hour was encountered, and PNCD was initiated, allowing drilling to immediately continue until target depth was reached. Downtime, of course, was minimized because MPD allowed for the immediate transition to drilling instead of mitigating or addressing severe circulation losses. No rig time was wasted mixing and spotting lost circulation material, which from a carbonate drilling standpoint would pretty much not do a whole lot in terms of mitigating severe losses. LCM is useful for slight losses, but for severe loss zones, the most efficient way of being able to do it would be to drill with pressurized mudcut drilling and MPD. It also kept H2S at bay and kept it away from the surface, increasing the overall safety of the operation, because all of the fluids and all of the cuttings and all of the gas were kept and pumped into the formations that were causing severe circulation losses. More importantly, the average section rate of penetration was increased by 5 times over that of a previous well in the block. So safety, efficiency in Angola with MPD in a carbonate formation. In clastic formations, it's not about severe losses, it's more about narrow mud weight windows and early kick detection or advanced flow detection, especially when you are dealing with high pressure, high temperature wells. In this instance, with our friends in Norway, for an offshore exploratory HPHT well, or high pressure, high temperature well. Production hole size was 8.5 inches, and the total depth reach was more than 5,900 meters. Section TD was reached within a narrow 0.4 ppg drilling window under extreme pressure and temperature conditions. An overbalanced wellbore was maintained, and ballooning and breathing events was immediately diagnosed and controlled by evaluating pore pressure and detecting kicks. 10 days of rig time was saved. That's a savings of as much as $7.5 million, not to mention the benefits in terms of reducing risk and enhancing safety. Gas influxes were controlled, and weighing up of the mud was done precisely and quickly, allowing savings over the use of conventional drilling methods. Lastly, MPD is a proven and tested solution in subsalt or pre-salt formations. In this particular case study, coming from our friends in Brazil, Bom Dia, in the Santos Basin, on a deep water vertical well that has already been abandoned with massive fluid losses while it was drilled. MPD allowed for entry of the said well, and through the plugs and abandonment devices that have already been installed, once they re-entered the well, the operator encountered a severe fluid loss zone that consumed 600 barrels an hour. That's why it was plugged and abandoned. MPD was used to re-enter, and once total loss of circulation was experienced, the switch to pressurized mudcut drilling was made, and the targeted production zone was reached, and completion was run, and essentially the well is now producing a whole lot of oil for our friends in Brazil. So whether it's carbonate, it's clastic, or pre-salt, subsalt formations, MPD is an accepted, proven, and expected way of drilling geological complexities. We have discussed all the rig types whether it's land, jack-up, semi-submersibles, or drill ships, that MPD has already been deployed on all of them. MPD is also applicable on all the phases of the life of the well, whether it is exploration, appraisal, development, or intervention. And it has proven that the benefits outweigh the costs for this technology to be used in all these stages. And it applies to all applications, and particularly to challenging geological environments, whether it's severe losses in carbonate formations, high pressure, high temperature clastic reservoirs, or through subsalt formations to be able to address risks and uncertainties. MPD is a technology that is reliable in all these instances. It has now been deployed in all the regions of the world, as you can see from the geographical, and geological diversity that was showcased in the case histories, of which, because we have limited time in this webcast, we were only able to discuss at least 7. There are more in the case history folder that is provided as a supplement to this webcast, where you will see the depth and the expanse and the range of MPD operations around the world, whether it be land or offshore, which is the focus of this particular presentation. MPD is proven, accepted, expected. We thank you for taking the time, the effort, and for the attention you have given our webcast on offshore managed pressure drilling. And we invite all of you to continue attending and participating in all the upcoming webcasts that we have. There will be 4. Webcast 2 will focus on readying rigs for a safer, more productive future. It focuses on how MPD technology is being integrated into the rigs of the future. That will be on June 2015. Webcast 3 is on onshore applications for August 2015, on land, as to how we are able to drill safer, faster, and smarter. And the final webcast, which will discuss how MPD is now the new drilling convention, will be rolled out on October 2015. We are more than glad to have you in this particular event, and we hope you will continue to support us in the subsequent events focusing on MPD, the new drilling convention. We are now ready to entertain questions, but for those who are able to miss this particular webcast session, please be informed, or please inform your friends, for those who are attending this webcast, that this is recorded, and it will be available for later on-demand sessions. And if they are unable to ask the questions that will be asked in a few minutes, we are still able to address their questions through the email address provided here, MPD Answers, and of course we will answer, at weatherford.com. Thank you very much, everyone, and we are now ready for questions regarding the presentation. We have a question here from Ahmad Ali Rafi, and the question is, what is the maximum pressure that the RCD can hold? Essentially, based on the standard for API 16 RCD, from a Weatherford standpoint, our rotating control device can hold as much as 2000 psi, according to API standards, if you require API 16 RCD. And this pressure reduces as you increase your rotational speed. So if you are rotating at 100 RPM while drilling, the RCD would probably be good for 1000 psi depending on the type of sealing elements on the RCD bearing assembly that are being used. However, this will vary depending on the type of RCDs and also on the models and the bearing assemblies that are deployed in relation to the equipment. On the Angola history case, the question is, how do you trip out of the well when you are having severe losses? Well, Weatherford has a solution for this. We normally use a downhole deployment valve, and it has been deployed a lot from an offshore environment. I've personally seen operations in Indonesia, and I've seen other offshore deployments of the downhole deployment valve in other areas. But essentially, if you're having severe losses in PMCD mode, being able to trip out of the hole safely would be a priority, and the DDV addresses that. Although there are other means of going out of the well, it will be far riskier compared to using a downhole deployment valve. Thank you, Cesar, for that question. We have another question on how many generations or versions of the system do you have now, and are you working on the new version? Being a technology company, we are always working on the new version, and the generation that we usually have or deploy are the ones that are fit for purpose for the application that it is going to get used. We do not cookie cutter solutions for our clients, and we customize it based on their requirements. Alastair Craven asked, what improvements have been made or are being made on management of heave effects to bottom hole pressure control, especially in harsh offshore environments? Heave, from this standpoint, will always be there, since from a deep water standpoint, the rig will always be moving in relation to the waves, but essentially by putting the RCD below the tension ring and below the termination joint, you isolate the telescopic joint on top, and diversion towards the MPD manifold is done with a greater degree of precision compared to conventional methods, allowing early kick detection in deep water. And we are looking at also sensitizing the MPD system to heave effects, and also looking at tying it into the heave compensation system of the rig to be able to address heave factors in the MPD system. Mario Campos has asked how long it takes to go from for MPD to go from preparation to implementation on a dynamically positioned drill ship. I would say 6 months, 4 to 6 months, if equipment is already available. However, we do need to take into consideration the interface between the rigs and the MPD systems that are going to be integrated into them. So just to be safe, 4 to 6 months. We've done it. We've visibly done it in that particular time frame. Although additional time would of course be preferred, so that lead times with regards to critical items can be properly addressed. What will be the key to choose the BTR, moored or not moored floating rigs? Essentially, for the below tension ring RCD, it normally is deployed when you are drilling using a dynamically positioned drill ship, mainly because we will need to be able to have flow lines from the MPD system to bring returns to surface. And if we are above the tension ring, we will be limited in terms of rotational capabilities. We have a comment from Brian Tarr of of which he says that the focus of the presentation is on drilling. There are tripping challenges introduced by CBHP and PNCD, and we acknowledge that fact, that there was a question asked about tripping as well in the Angola side. From a Weatherford standpoint, we do have solutions in relation to the same. And Brian subsequently asks, can these challenges be addressed by drilling with a liner or casing drilling system? My answer would be generally yes. We do like to look at a well from a well engineering standpoint as well. We do have, Weatherford also does provide well engineering and project management services. And we look at whether a technology is fit for purpose for a particular well, whether it's MPD, whether it's drilling with a liner, or with casing drilling systems. We look at it from a wholesome perspective. We do not prescribe to providing widgets. We insist on providing solutions. Alec has asked, does software deployment with the MPD system differentiate what is provided by Weatherford from other MPD providers? Well, from a software perspective, it's just like the software in your computer. There's always better software, and there's software which is not exactly better. Essentially, the proof of the pudding is in the eating. Weatherford systems, from my point of view, of course I'm biased, but I've seen the software deployed on the field and work as required, as prescribed, when I needed it. So based on my personal experience, the software and how it processes the information from a Weatherford standpoint is very, very applicable from an MPD deployment standpoint. What is the height required above the BOP for the RCD on a 13 and 5/8 stack? Essentially, for land rigs, which I'm assuming this is, or if it's a jackup, we essentially have different types of rotating control devices with varying heights. We're even working from a technology standpoint on a very short RCD, which we call compact, to be able to minimize the amount of space that is occupied by the RCD. If you don't mind, Steve, we will be sending you an email on the dimensions of the RCD that are available to be able to fit your requirements. A question from Abdul Sabur asks, when the drill ship rotates or changes orientation, how do you keep the RCD hoses stationary? Abdul, essentially by placing the rotating control device and the hoses below the tension ring, we are away from the tensioners that are in the way of the hoses, allowing us to be able to rotate more independently compared to if it were above, because you will immediately be limited by the presence of the tension lines that are there. If you'd like, we can provide you diagrams as well via email for details as to how we are able to accommodate the hoses in a deep water and dynamically positioned environment. For above tension ring applications, how are operator feelings or acceptance about circulating influxes through conventional risers? From a deep water standpoint, there are some operators that are open to the idea of circulating a small influx through the riser, and there are some who have actually done the same. But most of the operators we have dealt with are more reserved with regards to circulating an influx at full drilling rate through a conventional riser. However, I believe that if properly planned, if properly engineered, this particular maneuver is possible, and it has already been done. Perhaps with time and with with additional information, it will become more accepted and become the norm, become conventional, so to speak. Pedro Luz asks, what is the maximum internal diameter in the RCD? Well, in the RCD body, we can accommodate a pass-through of 18 3/4, allowing you to run your 18 3/4 test plug through the RCD body. But if the bearing assembly is installed, we will only be able to accommodate as much as 9.1 inches roughly through the RCD bearing assembly. How are you going to run and cement a casing on a pressurized mudcap drilling scenario? Essentially offshore, especially on a semi-submersible, being able to utilize the subsea BOPs for isolation purposes, we are able to use it as a lubricator that will allow us to run a liner that is run on drill pipe, to which we install the bearing assembly. So we are able to run the said liner to bottom once the BOPs are open, and then we are able to deploy the said liner even in severe circulation losses. Cementing the said liner is somewhat tricky. You will not get cement to surface when you are having severe circulation losses. But essentially, with the use of annular casing packers and the like, you should be able to run and deploy the same in a PMCD scenario. There's a paper that has been written and is available in the SPE archives specific to running liners in PMCD mode, which we can reference in relation to the same. Alex asks, what is the smallest influx volume that the MPD system has detected? Essentially, the system, from a default standpoint, is programmed to define an influx as 15 gallons per minute, progressing over 15 seconds. So the amount of influx volume that can be detected can be very small using the system. Roughly, with the well or the influx already controlled, you normally have a kick of around 1 to 2 barrels fully contained, even in a deep water environment. Brian asks as well, in a depleted reservoir application where the mud weight required to prevent losses can be lower than a seawater gradient, can constant bottom hole pressure be used in this type of depleted reservoir? Essentially, from this standpoint, looking at it roughly from an overall engineering picture, if there is a drilling fluid available that is lower than seawater gradient, and if ECD is within the range where it mitigates the said losses in a depleted reservoir, then the answer would be yes. It's ideal to have constant bottom hole pressure, but it will be a matter as to how depleted the reservoir is. And if a single phase fluid can still be used to be able to drill through it in constant bottom hole pressure mode. That being said, there are also other options with regards to multi-phase systems, but it will increase the level of complexity of the said operation, which will require additional engineering and additional discussions with the operator with regards to the comfort level they have regarding the same. We have time for one more question, and we will take it from Mr. Seb Olid, who asks, is MPD applicable to any kind of formation? And since varying formations may affect the pressure of drilling? A quick answer would be yes. We've seen MPD deployed on all types of formations, even on unconventional resources, to be able to optimize drilling through the said formation. So from a formation or geological complexities standpoint, Seb, yes, MPD can be deployed on any type of formation. That being said, we do need to provide proper engineering and evaluation of the application before you proceed with using MPD. Like everything else in the world, There is no one solution that cures all. MPD is not a panacea. However, it provides options in terms of increasing safety, efficiency, and drillability options for everybody involved. That being our final question, we thank everybody for taking the time to attend this webcast. And for those who asked questions, we will be answering all your questions offline. So don't worry if we were not able to answer it during the webcast. We will be answering your questions in detail via email after this webcast. Thank you, everybody, and we wish you all a good day.